magnetic induction or magnetic flux density, also known as magnetic flux density. Magnetic flux density, also known as magnetic field strength. Magnetic field strength. And this is represented with capital B. So, when I started teaching you magnetism, we had a bar magnet. And we said, if you have north and south pole of a bar magnet, there's a field that runs from north to south outside the magnet, and from south to north inside the magnet. And this field gets concentrated more at the pole. So these were the things we've talked about. And what I'm drawing now is not strange to you, except you are just joining. Or you would have also been taught in your secondary school. So now, this is the magnetic field. When you talk about magnetic field strength, you're just talking about all these magnetic field lines. And I told you that the strength is always more at the pole, Abby, when we did the experiment. I told you that you can determine that using iron filings and a compass, if you still remember. So, but if you have been practicing, you should have gotten used to it. We have been doing it for almost like 3 weeks now. So there's no way you carry your book every day, you revise that by now. So now, after that, I now told you something like this, that let's imagine we have a coil. I told you if a current is flowing in this coil, then field will be generated. Now, if the current flows anti-clockwise, the face of the field of this coil is going to be what? I like as you are keeping quiet. The face is going to be north, Abby. So when the current is flowing anti-clockwise. Now, if the current flows clockwise, I said the face is going to be south. So these were the things we have done before. Now, if you notice everything I've always been talking about all this while, we said something that if a current is flowing in this straight wire, there will be there will be magnetic field generated. Abby, you still remember that? That if a current is flowing up, we have used a lot of rules, right hand grip rule, Fleming's left hand rule and all. So if a current is flowing up this wire, magnetic field will be generated. So everything we have been doing all this while, and which was the application you studied yesterday, was that we always use electricity to generate magnetic effects, magnetism. That's what we have been talking about all this while. Anytime current is flowing, there's a magnetic field. We talked about it in a straight wire, we talked about it in a solenoid, we talked about it in a coil, Abby, and we have talked about how all of those fields operate. Now that we have this understanding, we want to do something like the opposite. Now, current is not going to flow. I'm going to bring magnets. But that magnet that I'm bringing will generate current. So our focus in this aspect is that we are using magnetism to generate electric current. Our previous experience was that we use electricity to generate magnetism. But now we want to use magnetism to generate electricity because it has its application. You switch on your generator, your light comes on. You switch on lights, your fan comes on. So the one that is using light to turn to fan, to rotate, is what we have been talking about this while. And we should have expressed the applications yesterday, but I know you have read it. So The one we will now want to talk about is how we are going to use magnetism, how you are going to use your generator. How do we have light? There was light, and that light made fan to work. Now, how do we not have light, but we are going to generate light? So we want to generate electricity. What NEPAs used to do in their office, that they used to supply you light, is what we want to study now. But that light they supplied you that makes your fan to work is what we have been studying all this while. So, and if you had actually done the assignment, you would have appreciated it better. So now, let's do this. In order to now understand this, I said I want to use electromagnetic induction. I want to use magnetism to generate electricity. So that's the purpose of this class. And this experiment was performed by Faraday. So Faraday realized that, let me start in a simple manner. You take a coil. This coil is not connected to a battery. If you start electricity normally, you connect a battery, then you can connect your bulb or whatever you want to connect. And when you switch on the electricity, then bulb will come on. All because battery was here. But if there was no battery and you just connect wire, you connect wire to bulb, the bulb will not come on. So, but in this case now, this is wire. I've connected wire. There's no current. There's no battery. Nothing is happening. But I now brought these magnets. This magnet has a field around it. The fields are numerous and whatever it is. So from my experiments performed by Faraday, Faraday now realized that this thing does not have battery. But by the time he starts moving magnets towards the coil, he starts seeing current flowing in the wire. He moved the magnets away, current was flowing in the wire. But when he did not move the magnets, there was no current. That was his experiment. So he was wondering what is happening. So he noticed something. He now connected a galvanometer. A galvanometer is an instrument that is used to detect current, which you have read yesterday. So now, when you move this thing, then you notice something. You notice that this galvanometer shows a deflection. When it's moving it out, you notice the deflection went in the opposite direction. So you now realize that, oh, even if there is no battery, as long as all these lines are cutting through a wire, so as long as the lines are cutting through wires, then there will be current generated. So all of these lines is what we call the strength of the magnet. Then when those lines enter a particular space or area, then it becomes a flux. The strength of the magnet, which is the number of the lines that can enter a given area, gives what we call magnetic flux. So, for definition, the first thing you need to know is that magnetic flux is given as the product of magnetic field strengths or the number of magnetic field lines entering a given area. That is what magnetic flux is in definition. The product of magnetic field strength or the number of magnetic field lines entering a given area. So that is the definition. Meaning that physics is not something that you don't have to write those definitions because they can ask you. So phi is equal to BA. What does B represent? The number of magnetic field lines. Abi, A represents the area it is entering. If this coil is very small, then only few of these lines will enter. If the coil is very big, then more of the lines will enter. And the number of field lines that are entering determines the magnitude of the current you will experience. If a battery is 12 volts and a battery is 6 volts, you don't expect them to work the same way. So, from what we have said, just understand this first. Magnetic flux is given as what? The number of magnetic field lines entering a given area. So let's start from there. Now, another question they can ask you is B is equal to phi over A. And this B equals phi over A, they ask almost all the time. They are units. They can ask you that what is the unit of magnetic field line or magnetic field strength? The unit is Tesla. Tesla. And that Tesla is also known as Weber per meter squared. So this guy, the unit of this guy is Weber. The unit of flux is Weber. Symbol WB, Weber. The unit of area is meter squared. So if you say magnetic flux density, the unit is going to be Weber per meter squared. Is that taken? But that Weber per meter squared is a bit mouthful. So you can just call it Tesla. So the unit of B is what? Tesla. So they can ask you. And they can put them in Roman numerals. That's number one question they can ask you. Then, let's now move on. So what did Faraday now do? So Faraday now gave us two laws. So let's focus on Faraday's experiments now. Faraday now discovered that if he moves the magnets in the coil, so there is a coil and there is a magnet. And this magnet, when he moves it into the coil, there will be current flow. So the arrow that I'm drawing here now, so let's call this one experiment A. So for Faraday's experiments, when he moves the magnet into the coil, there will be current flows. And the current that is flowing in this coil will act in a way to oppose this that is producing it. So listen carefully. Now, there is no battery here, if you can see. But when I move a magnet, I'm going to cut some things through this coil. What am I cutting through the coil? All these lines, Abby. Now, that line is called the magnetic field strength. Then the region I'm passing it through is the area of the coil, Abby. Now, when this coil enters, there will be current flow. Now, Faraday now states that in his first law, or just stating his one means. So look at this. Same magnets of equal strength and this. Now, between A and B, which, if they are moving at the same rates, this guy and this guy are of equal strength, but the coils are different. So if I ask you a question, out of the two of them, between A and B, which one do you think more EMF should be generated? Can you defend that? And why? Because there will be a lot of flux because there's enough space. So there will be a lot of flux cutting through that area. Do you get the point? So Faraday is now stating that the magnitude of the induced EMF, that means the strength of the current that will flow inside this place, will be directly proportional to the rate of change in flux. So the rate at which you are changing the flux. So the more the area, imagine that all of you want to enter this space at the same time, and all of you want to enter that space at the same time. And we call it influx, Abby. Like your flux, you want to flux inside. All of you want to rush inside at the same time. You will easily enter here compared to that side, Abby, because the area is what? Bigger. I hope you're getting my analogy. So now, from that just explains Faraday's law. So Faraday's law states that anytime there's a change in flux, there will be an induced EMF. And that induced EMF will be more if the flux is changing at a particular rate. So now, mathematically, that statement we just talked about, Faraday now says that the EMF is going to be directly proportional to the rate of change in flux. And you know when it involves rates, there will be change in time, Abby. So it's direct proportional to the rate of change of flux. That's Faraday's law. And that E is equal to N d phi dt. Where does N comes from? The number of turns of the coil. It's not just one coil. I want to make it simple. That's why I'm just using one coil. But the coil can be, if you go and open many of these electronics and you see coil when they wire it, especially around the transformer and all of those things, there will be a lot of it together. So there are several number of turns of the coil. So N represents the number of turns of the coil, number of turns. And you can see that E and N, they are directly related. The higher the number of turns, the higher the EMF. Phi represents what? The flux. Abby, what's the unit for flux again? Weber, not Tesla. It is Weber. Please, is that taken? Flux. There's a difference between flux and flux density. There's magnetic, I wrote it, magnetic flux density, and there's magnetic flux. Magnetic flux is the symbol phi. Magnetic flux density is the symbol B. So if they ask you that what is the unit of magnetic flux, it is Weber. What is the unit of magnetic flux density? It is Weber per meter square or Tesla. They ask these questions as students man before. So you know the rest. Now they can even give you a question and they will tell you that N is equal to phi 2 minus phi 1 all over T2 minus T1. So that is Faraday's law. Now, when you see this formula, the formula usually comes like this. Please follow. This understanding will make you understand transformer, how transformer works and everything. So the formula, whenever you have it, it is always written as E equals minus N the phi the T. And where does the minus come from? Let's talk about it. That's Lenz law. So the one we just talked about is Faraday's law. There's an induced EMF whenever there's a change in flux. And the rate of change in flux will be directly proportional to the magnitude of the EMF. Now, Lenz law. One thing we noticed in our experiment, so that you will understand the definition. During Faraday's experiment, he noticed something. He was moving a magnet north and south towards the coil. Then, as he was moving it towards, the current was going in this direction. And if current is going in this direction, you already know what that is. That means this is north. Abby? Look at this coil as if it's standing like this, not like this. You remember we have always been doing it. It's not slipping. So it's facing the magnet. So let's say this is the magnet. This is the coil. So the magnet is entering inside. So as the magnet is entering inside, the coil will generate something inside, a field. And that field generated inside the coil always opposes the motion of this guy. What is generating the current? The movement of the magnet, Abby. But at the end of the day, something is also generated in the magnet due to the movement of the current, where we started from. If current is moving anti-clockwise, then field will be generated. But that field generated is always opposite to what this guy is doing. That's where Lenz law comes in. So, Lenz law is now telling us that, oh, there's an induced EMF, but the direction of the induced current, otherwise known as the induced EMF, always acts as to always oppose the motion that is producing it. So this guy is going inside. but this guy will generate the EMF in such a way that it will repel this guy. So that's experiment 1. You can see my arrow. Now tell me what this one would be. Share one. So let's manage this. Now let's imagine this is what I'm doing. If you have been following my explanation. In this scenario, my question mark should be what? The direction of the current should be what? Clockwise. If you have been following what we have been doing, it's not always difficult. So can I rub this part? When you get to university, you realize that people do not know anything. Now, this is what I'm doing. I put a question mark here, but this is my arrow. According to Faraday, I'm moving this guy away. As long as I'm moving it, I'm changing the flux. Because as I'm bringing it, there will be a lot of the lines. And as I'm going out, the lines will be reducing. Abi? So you expect the EMF to also reduce. Now, as I'm moving this guy out, something will be generated here. And from what I explained, according to Lenz law states that the direction in which the current will move here always acts in a way to oppose the motion of this guy. So meaning that as I'm moving this guy out, this guy will generate something that wants to bring it back. So what do you think will be in my question mark? Because what is going away from it is north. So you want to create south here so that it pulls it back. And in that case now, you already know the direction of the current. It is going to be clockwise. There was no current, but after you have generated the field, you had current. So how about this case scenario? Everybody, what would be my current? Current direction. Is it clockwise or anti-clockwise? So it's going to be south, Abby, and it's going to be clockwise. You understand that? Because what I'm bringing in is south, and this guy always acts in a way to oppose what you are doing. So that's Lenz law. So let's define Lenz law. I hope you are following what I'm doing. It's not to read stories. Have understanding. So Lenz law states that the direction of the induced currents, you can now open a bracket, that is the induced EMF. They can say induced currents, they can say induced EMF. The direction of the induced current, that is the induced EMF. Please, anytime they are teaching physics, always pay attention. Physics is not difficult, sincerely. And no matter how you read, most times, you can read chemistry over and over, and you can have confidence that you know chemistry until the day of exam. You will know that you don't really know chemistry. Physics is more like maths. When you know maths, you know it. But the journey to knowing maths is tedious. You must have solved a lot of questions before you get used to maths. So that when you see it, you already know the approach. When you see it and you don't know it, you don't know it. But biology and chemistry, you can still guess. I feel this is the answer. Whereas you are picking wrong answer. But you are still going with the confidence that I feel this is the answer. But for physics, you might solve it to a level that if you don't get the answer, you know that, oh, I'm wrong. And you'll not be scared. But those ones you can guess, you are only guessing, you are not sure. But there's something at the back of your mind will tell you that at least I chose something. And it will give you confidence that you did it well, whereas you probably didn't do it well. So if you write an exam, most times, if you prepare well, you will see that physics is always easy for you to score 100. Oh, more money. It's very easy. So don't be scared. Chemistry might look simple, But all you just have to do with physics is practice. If you drop physics for a while, it will also drop you. It's just like math. So practice. Chemistry, you can wake up anytime. If you have known chemistry, they can ask you some things and you will think about it and you get your answer. But if you drop physics, bó ṣe ń drop ẹ̀ ló náà kọ́ èyí sí ẹ, ó náà lọ tiẹ̀ nìyẹn. So get used to it. And there are some things in physics that if you do not know before, some other things will look difficult. That's why you should not be scared. What I'm saying now, if you don't know some things before, what I'm saying now might look difficult to you, whereas it's very simple. But please, practice. It's not hard. So, the direction of the induced EMF, that is of the induced current, so I didn't put current here, of the induced current, that is the induced EMF, always acts as to oppose the motion, What is that motion now? The flux, Abi? As to oppose the motion, that is the magnetic flux producing it. The direction of the induced EMF or the induced currents always acts to oppose the motion producing it. What is producing this one? This guy. What is this guy doing? He's creating a field that will oppose what this guy is doing. Are you following the step by step? So now, this common question every year that if you are writing mock, you will see in your mock, and when you come back, you tell me you saw it, is that they always ask you that Lenz law is also known as law of what? Lenz law is also known as law of conservation of energy. This law is also known as law of conservation of energy. You are using mechanical motion, electrical energy, and all of those things. So, this is the basic analogy. Now, this has application. The application is seen in alternating current generator, DC generator, transformer, your carbon microphone, your induction coil, and all of those things. So let's take them one after the other. Now, let me derive some formulas for you again. So if they ask you that, why is this negative there? The negative is representing Lenz law, meaning that the EMF generated is opposite to the flux. Again, that's what the negative means. Now, you remember that flux is equal to BA, right? And E is going to be equal to NBA over dt. It can be changing VA and all. Now, area can be length times breadth, right? So I can say, depending on the coil, there are a lot of things that can change. I can say NBL LB for whatever case, like breadth over time. Abi? Now, breadth over time is just like saying distance over time, and that's velocity. So that means I can say E is also equal to NBLV. Do you get that? So NBLV, V is velocity at which you are moving the coil. L is the length of the coil or the length of the wire. While B is the magnetic field strength and N is the number of turns of the coil. Now, our experiment does not end here. You can move the magnets and you can as well move the coil. So let me show you something that they can also ask you. I know you're an examiner, but I've been working with your examiner for over 15 years. And I know what they can ask you. So, another thing is, you remember this solenoid. I'm probably just going to do one. Then I have a galvanometer. I'm not even going to do one. You are going to do the rest. So there's a galvanometer here. What does the galvanometer does? To detect current. So which means there is no battery here. You remember what we did before was that we put a battery, a DC, and that battery sent current. And when current started flowing, this guy became a magnet. If you remember, we produced one of the magnets then. But now there is no battery. So how will current flow? This current will flow when you bring a magnet, according to Faraday. So when you bring a magnet, let's say I'm bringing knot. Please understand this. When you observe it on your screen, on your exam day, analyze it to pick your answer. What I'm drawing here, I'm not using any book or anything, and it's not because I've seen this somewhere. I'm just doing it as it's coming. So analyze it. What I know is my analysis is what I want to talk about. So don't say, Sodium said it will be to the left, it will be to the right. There is what it will follow if you read textbook. But as much as possible, while learning too, I never cram textbook. I try my best to understand the best way I can. And if I don't, I will keep reading until I do. So now I'm bringing knots. This is a coil now. I'm bringing knots of this guy into the coil. Why bringing the knot of this guy into the coil? You know, normally there's no current. But by bringing the coil, bringing the magnets, there will be a change in flux, Abi. And as there's a result of change in flux, there will be an induced EMF. That means there will be an induced current. Current will flow. And how do you now know? This guy, when current starts flowing, this guy will become a magnet, Abi. And now, when it becomes a magnet, what should be the side of this pole and what should be the side of this pole? From what I've shown you here, definitely you know this side is going to be what? And this side is going to be. Now, let me take you back to where we started from. Whenever current is flowing, I said you can use your right hand grip rule. Abi, your thumb points where? The north, Abi, while the cord finger points in the direction of the current, Abi. So now, for this now, the knot is here, so my thumb will point there. So I wrap it around this guy, meaning that the current will keep going up, up. Then if it keeps going like that, then it will come down and it will go up. Hope you're following. So the question they can now ask you is that this galvanometer arrow, where will it deflect? Will it be to the left or to the right? It will deflect to the left because of the direction of the current. Are you getting this? So it's going to push it this way. And by the time it moves that way, you said it has been deflected to the left. Don't cram this. When you solve questions, apply it. Apply it when you solve questions. And if it is a coil, you will also know when you are solving questions. So let's move on. If I change it to south or north or anything, you should also be able to tell. You tell from all the stories we have been doing. How did we know this? We know that we already know from Lenz law that anything this guy does, this guy does the opposite. And we also knew from what we have started with that if current is flowing in this guy, magnetism will be generated. But now magnetism is inducing current. That current is also invariably inducing magnetism. And that magnetism is acting to oppose what this one is doing. So that's a combination of several knowledge. So you using this one, you knew what will happen here, and you knew what the deflection will be. So if you just look at it, and you can't tell a whole lot of stories from it, you might not know what the deflection will be. So they can ask you, will it be deflected to the left or deflected to the right? Now, from this one, I knew this would be not. And for this one to be not, I remember my rule that states that for I to know the direction of the current, I grab the wire, Abi. I remember we did all of these things. Then my thumb will point where the knot is. If the knot is here, then I will grab the wire like this. Then my thumb will point here. And so grabbing the wire like this means my fingers are up, they wrap around the wire, then the current keeps going up in the coil. And as the current keeps going up, at the end of the day, if you follow that trend, it looks like it's going like this. And if it goes like that, then it will hit this guy. And at the end, this guy will deflect like this. Do you get my point?
Yes.
So the only person that might not be getting the point might be someone that is just joining. And you can let me know. Who said no? You said no. Who said no? What points don't you get? You might actually not get this other part if you were not in the previous classes. And the videos are even, I think the video is on YouTube. All the ones we have done before, they are on YouTube. So even if you just joined today, you can go and check Primax YouTube. Please, precious. Let me to pass it to the back. So now, that's the only reason. But if you were in the class, you should get what I'm saying. But it's not a problem. You know, knowledge and knowledge, knowledge and knowledge. I used to tell you, the problem some people used to have is coming late. But it does not matter now. The fact that you came late does not mean you can't still score your 100. Shall get what I've said. Some things might not be so clear. Yes, meet someone. Then the person will now explain further after the class. Because going back to some things now, we look as if so just, but if you know you were in the class and you still didn't get what I've said, I can explain further. But even if I explain further and you were not in that class, you might not really get what I'm still saying. So go and watch it on the YouTube live session. They are still there. And I named everything. Magnetism, all the classes are on our YouTube from beginning to the end. So take your time to learn it if you want to learn it. So, and if you don't have time to learn it, meet with someone to teach you. So, but one thing I want you to note is that when will there be no deflection? There will be no deflection when both the coil and the magnets are stationary. When the coil and the magnets, there's no movement. That means there's no change in flux. When they are stationary, there will be no currents. There will be no deflection. There will also be no deflection when you move the two of them at the same rate. The rate at which you are moving the coil is the same rate you are moving the magnet. Then it looks as if it's still stationary. So when you move both of them at the same rate, then there will be no deflection. So, but when you move one of them towards the second one, is either you move the coil towards this guy or you move this guy towards the coil. When you do that, there will be currents induced. So those are the things you need to know. Now, let's look at the applications. So I'm sorry, I wish I explained better to those of you that are just joining, but some things cannot really be explained if you have missed some parts. But we will still go over this again, so just try your best. I wish there is time. During marathon, we used to go over it over and over, but I might resume my classes by March. So that's why I want us to spend our February judiciously, while my people will do the rest with you. So this Saturday, you can have organic and inorganic, maybe for like 2 hours at least, so that you practice it, so that there will be enough time to keep practicing. Now, applications. Number one application of what we just said is in generator. So we have AC generator and DC generator. Please, there's electric motor. Electric motor is that one of yesterday that you read. But generator is what we'll do today. So generator, then we have transformer. Transformer make use of the application. Then we have your carbon microphone. Carbon microphone. So they can ask you that all of these things, which one use the application of electromagnetic induction? You should know. There is induction coil and so on. So starting with generator. In the power station, what NEPA does is that they drive a turbine. There's something like a giant magnet. They rotate the magnet using waterfall or some things. Then by the time the magnet rotates, it will generate EMF. Just like magnet is cutting flux, it will generate EMF. That EMF will be turned to a higher value and sent to CT using a transformer. Generator generates the EMF. Transformer steps the EMF up or steps it down and send it to the community. When it gets to the front of your house, it steps down, then send it to your house. So those are the things we will look at tomorrow. And we'll complete, I will try and complete everything magnetism tomorrow. Then we'll move on to the next topic, AC circuit. So go and solve questions on what we have done so far and keep practicing. Then on Friday, you will have tests on everything.